Vehicle safety. By the end of the session, you must be able to solve problems related to vehicle safety, focusing on the relationship between the speed and the stopping distance. If we consider the formula, final velocity squared is equals to initial velocity squared plus 2 times acceleration times the change in position or the displacement. For a stopping car, the final velocity is 0. Then our formula becomes the final velocity squared is equal to 2 times acceleration times change in position. Two and acceleration are constant, so we can represent that by k. So this leads us to conclude that the final velocity squared is directly proportional to the change in position, or the final velocity squared is directly proportional to the displacement. That is, when the velocity doubles, the change in position quadruples. Stopping distance consists of the reaction distance, which is the distance the vehicle covers while the driver reacts. In other words, we can talk of the time between the realization or seeing an object and putting on your foot on the brakes. This is called the reaction time. 2, the braking distance. That is the distance it takes for the vehicle to stop after the brakes are applied. Let's do that through work example. A car is moving at 20 meters per second and the driver applies the brakes, causing the car to decelerate at 5 meters per second squared. How far does the car travel before stopping? We are given the initial velocity, which is 20 meters per second, and the acceleration, which is negative 5 meters per second squared, and we are asked to calculate the distance covered. The formula that we can use is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times change in position. Substituting, the final velocity is 0, the initial velocity is 20, so we square that, plus 2, the acceleration is negative 5. Note we are told that it's decelerating, and then we have the change in position. So making the change in position the subject of the formula, change in position is equal to 40 meters. Worked example number 2. A car is moving at the speed of 25 meters per second where the driver sees an obstacle on the road. The driver's reaction time is 0.8 seconds, meaning it takes that long before the driver applies the brakes. After applying the brakes, the car decelerates at 5 meters per second squared until it comes to a stop. The car was moving at uniform velocity of 25 meters per second for 8 seconds until the brakes were applied and the car came to a stop. That is, the car was decelerating at 5 meters per second squared. Calculate 1. The reaction distance. 2. The braking distance. 3. The total distance. The reaction distance. During the reaction distance, the car is moving with uniform velocity of 25 meters per second. Hence, we use the equation for the definition of velocity, which is the velocity is equal to, or we can say the average velocity is equal to the rate of change in position. Substituting, we get the velocity is 25 meters per second and the time is 0.8 meters per second, making the change in position the subject of the formula. Then we know the change in position is 20 meters. Braking distance. We know the final velocity and the initial velocity and the acceleration of the car. Hence, we use the formula final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the change in position. Substituting, Initial final velocity is 0. Initial velocity is 25, so it's 25 squared plus 2. And because it's decelerating, acceleration is negative 5. And then we have to calculate the change in position. So making change in position the subject to the formula, we get 62,50 meters. Then lastly, adding the 2, that is 20 meters plus 65.5 meters, you get 82,50 meters.